Hello, my name is Ahnaf. Project is design and simulation of a PV system to power reverse osmosis unit of a house, and I will be conveying my presentation today. The main objective of my project is to power up the um, reverse osmosis unit of a house. We need to know what a reverse osmosis system is. It is basically a system where we can desalinize water. The water is firstly transmitted through a semi-permeable membrane, and they are the insoluble particles that are present in the water, mostly magnesium, chlorine, etc. They will be filtered through a semi-permeable membrane, and the desalinized water will be delivered to the water reservoir that is placed on household. And to power up this whole system, we're going to be using natural resources. For this project, I'm using solar resources to power up the system. For this reason, I'm going to be using a PV panel. So my primary objective is to power the reverse osmosis unit of a house using PV panel. And basically, to power up the PV system, we need maximum power point tracking. So my secondary objective is to make sure that the harnessing of the power of the solar panel is being done properly. So I'm gonna be also doing some simulations of the maximum power point tracking of the system. So the whole project can be divided into two parts. One is the powering unit, that is the power that we harness through the solar panels, and the other one is um, the reverse osmosis unit. So I have to follow some steps to follow the usual procedure of developing my project. The first one is we need to do the sizing of the PV panels, and the PV panel is connected with some batteries as backup in case the solar panel fails to operate. We're going to be using batteries in for unfavorable conditions, and they're also connected with some inverters. The inverters are converting the DC power to the AC, and on the other side we have the arrow membrane. For the arrow membrane, we are using a feed pump. The pump is powered through the solar panel, and it intakes water from water sources, and it passes the water through the semi-permeable membrane, and finally the water is salinized and passed through the water reservoir that is placed in the household. And the whole system is designed so that we can see whether um, the power that we are using to operate the RO system, whether the whole harnessing of the power is being utilized properly. Main objective of the system to make sure that the usual procedure is being conveyed properly. We have to size the PV panels and the RO system, and I'm gonna be using multiple simulating softwares to demonstrate that. Basically, this is the block diagram of the system. Here we are using a solar panel as the power sources. We're using maximum power point tracking. We're also using batteries in case the solar panel fails to operate. The batteries will give backup power. We're connecting the powering unit with an inverter. The inverter is connected with a feed pump. The feed pump intakes salinized water. It passes the water through an arrow membrane, and the arrow membrane converts the salinized water to desalinated water, and finally um, sends transfers the water to the reservoir tank that is situated in the household. And there's another part that is the concentrated brine. Some water cannot be purified by the arrow membrane. Depending on its permeability, some portion of the water cannot be salinized, and that is called concentrated brine. It can, the concentrated brine can either be recycled, or it can also be not used, or um, can be thrown away by the consumer. In my project, I have not recycled the concentrated brine because the specifications of my arrow membrane does not support the system of the purification of the concentrated brine. These are some of the data that I have gathered from the Homer software. It is seen that the average irradiance in my region is around 4.6 kilowatt hour per meter square, and the average sunshine hour is around 5.8 hours per day. So for this reason, I'm gonna be using a pump of around 100 watt. It should be operating around 8 hours, so total 800 watt hour per day. And if I consider an overload of around 50%, the wattage would be around 1200. So after calculating, it is seen that I will be needing two PV modules to convey this whole project, and the string size should be around 100 ampere hour. I have used some softwares to show the configuration of the solar panel system. On the left, I have used a to show how the solar panel is connected with the load. Here I have connected the solar panel with a battery charger. The battery charger is connected with a battery. The battery is connected with a boost converter. The boost converter is basically used so there is a protection of the battery and there are no unnecessary discharge from the battery to the load. And finally, the boost converter is connected with the load. And on the right, I have used MATLAB. I have embedded some codes and I have used some filtering to get my desired output. The details of the configuration is explained in my project. So this is a data that I have gathered from the WindFlow software. I have used the feed capacity that is used in my household. In my house, around 250 liters of water is consumed per hour by each person. So I have used an arrow membrane which has a feed capacity of around 250 liters per hour. The recovery rate is around 45%. Basically, the recovery ratio is more, but in due to the current geographical condition of my house and the um, other relevant issues, the recovery rate is comparatively low. The concentrate recycle percent is around 20, and there is also a feed bypass that does not flow through the arrow membrane. Rather, it is bypassed directly to the water reservoir of the house. The percentage for that is around 30%, and I have used a pump which has an efficiency of around 75%, and the distance head is 150 meters. So I have used a software, and software I have used a simulation system where I will be flowing water through an arrow membrane. I've used around 243 liter of water through the system, and for 243 liters, the feed bypass is around 73 liters, and the pump bypass is around 76.83 liters, and the concentrated brine is comparatively higher, which is 93 liters. And finally, the desalinated product is 150 liters. This is the demonstration of the simulation that I have discussed in the previous slide. Here it is seen that around 243 liters of water is initially flowed through the air membrane. A certain percentage of the water that we call the feed bypass directly gets accumulated in the product region. It does not get it does not need to be transferred through the air membrane. Another percentage of the water passes through the pump and then gets passed through the air membrane. In this case, among 243 liters, around 76 liter of water gets purified and then gets accumulated with the previous feed bypass of around 73 liters, and a total of 150 liters of water is restored on the as the product, and around 93 liters of water is the concentrated brine, and around 194.21 liters of water is passed through the water pump. In case of the MATLAB simulation, I have set an ambient temperature of around 25. I have used some embedded codes, some logic systems in the in my MATLAB simulation. It is passed through multiple filters, and finally we get the output on the scope. The details of the MATLAB simulation has been explained properly in my project report. These are some of the outputs that we have gathered from the simulation. For the maximum power point tracking, it is seen that initially the voltage measurement was around 360. After that, it um, decreased to 355, and it is fixed till the advancement of time. The buck converter, the the current measurement is somewhere in between 1 and 1.5 into 10 to the power minus 14 ampere, and the voltage measurement is around um, initially it's around 550, and then it gets set in around the 350 voltage. The product is seen to be around in between 0 to 2, that is 1 into 10 to the power 4 kilowatt per hour. It is seen that with the time the solar irradiance also decreases because the intensity of sunlight has an impact on the solar irradiance. For the protection of the system, there are basically two parts, the DC part and the AC part. For the DC part, we're using an miniature circuit breakers. We're using surge suppressor in case of lightnings, in case of if the solar panel is placed in an open area. For that issue, we are using surge suppressor to save the solar panel from lightnings. We're using switch disconnectors. There's relays as well implemented in the system, and finally it is connected with the inverter. And in the AC system, we're using an isolator followed by some surge suppressors and some miniature circuit breakers for this AC system as well. We're using some residual devices and metering devices to see whether the power transmission through the whole system is flowing appropriately, and finally the system is connected with the load. Well, the project has some impacts on solving social and technical challenges. Solar energy can be used as a great alternative power source. Solar-driven desalination technologies can supply a few to multiple liters of water per square meter, depending on its configuration and location of the place. The longevity, low cost maintenance, and easy installation and low operating costs can make the system play a major advantage for um, countries mostly situated in the tropical region like Bangladesh. It has some limitations. Firstly, the system is designed to operate under solar irradiance of around 4.6 kilowatt hour per day, but unfortunately, the weather of our country is unpredictable. For this reason, we could not harness the maximum power out of the system. We had to be satisfied with whatever we were that was available in nature. And due to the lower power consumption, as the we know that um, the RPM of the motor depends directly on the power that is supplied uh, by these power sources. So as we were unable to harness maximum power, for that reason the motor speed was low, and ultimately the feed flow rate decreased, and ultimately for that reason we were not able to get appropriate amount of water per day. These are some of the references that I have used for this project. That concludes my project. If there are any queries, please feel free to ask me. I will be available anytime. Thank you.